This is known as the can crush. And this is very, very well known. So, but this is a fairly complicated setup here. So let's see if I can get you to actually look at this thing a little bit better here. So what I want to do here is that I want to go in and I really want to look at something that goes something like this here. Let me see if I can. So here, I'm not prepared, it turns out. Let me go and see this. I needed an applet that I wanted to show you. Let me see if I find it. I hope I do, because I need that applet. Yes, I found it. Okay. That's what I want. So here. So let me do this here. And this is not what I really want to see here. So all I'm trying to do here is that I'm starting to just look at states of matter here. Okay, so now let me get back to what I was trying to talk about. So here's some really cool physics here. Oh, damn, I just lost my pen someplace. Okay, so now here's what I want you to think about that. I want you to, so air, maybe I should write this in capital. Air is a really good thermal insulator. And when I say a thermal insulator, what this means here is that it doesn't allow heat energy to move easily. So if you have an ice chest, we say that the ice chest is a good thermal insulator. So therefore, if something that you put in there is cold, it's going to stay cold. Okay, and that's what we mean by that. So now what we want to do here is that to give you an analogy of this thing here, think about a coffee cup, or let's say about a coffee container, one of those fancy containers that people buy here. And what you'll see here is that it looks something like this here. So if you have one of these coffee containers, of course it has a lid on that. But one of the things that they do here is that they're typically double walled. And they even make them out of metal, actually. And the thing that's really special about that is that right in between the double wall here, you know what they have? They have, right in here, they have either air or no air. Air works totally fine. And then inside here, you could put in your liquid that you want. You could put in a cold liquid, you could put in a hot liquid, either way. And so what you're finding here is that in this case here, what we say here is that the air stops heat transfer from inside the cup to the outside air. So what you want to do here is that, you know, by the way, have you ever noticed that if you make ice cubes and you have an ice cube tray, what you find here is that ice cubes, or if you make popsicles, they take a long, long time to freeze. Why is it that they take so long to freeze? It's because the air in the freezer is a really good thermal insulator. So it takes a long time. So if you really want to freeze something quickly, like there's units that you could buy to make popsicles, and they remove all of the air. And so what you find is that they only put metal around them. And you can actually freeze popsicles in most 10 minutes. You could literally freeze popsicles in 5 to 10 minutes without a problem. In fact, we have one, and it works amazingly fast. So let's get back to the point here. So here's what I'm talking about. If you want to change the temperature of something quickly, one must remove the air. You don't want the air at all. Okay? You don't want the air at all. So here's what we're going to do. We want to do a can crush, which means that we need to change the temperature quickly. So the first thing that we do is we got to remove the air. So now, the way we do this here is that we place a tiny amount of water in a can, an aluminum can, and bring it to a boil. So in other words, what you're really doing here is that you have the following thing. You have a hot plate, right? Here's the hot plate. And what we know about the hot plate here is that the hot plate, of course, is going to produce heat. So then you're going to take your can in here, right? So now you're putting your can in here. So let's say that this is your can. And I'm imagining an aluminum can, maybe a soda can. And so now what you're doing here is that you put that little bit of water down here at the bottom. And so now what happens? You're getting heat flow into the can. So now what you're finding here is that the boiling water creates steam. Which pushes out the air. So and so what this implies here is that now we have a can full of water vapor. Now it turns out, so this is good because water vapor can change temperature quickly, not like air. And so now here's what you get. So the end result is this. You would now have a can, right? You now have a can. And what you find here is that in that can, you have water vapor. And that water vapor is banging up against the walls of the can. And then the outside, of course, is atmospheric pressure. So again, this is atmospheric pressure. And then inside you got that hot water pressure. Now, here's the miraculous thing. So if I look at an image of this thing, I have an applet that I want to show you. And, you know, this sucker is just not heating up fast enough for me. Here, I'm going to try to see if I can do this thing. This must be the right one, wrong one. Oh, so it looks something like this here. So what I'll do here is that I'll come and I'll share my screen with you. So you could imagine that this is my water vapor here. Water vapor is more complicated than this. But let's say this is water vapor. And so these guys are just bouncing around, you know, all over the place. So if I look at this can here, this is what I'm seeing. Right? So now I'm going to go take this into here and I'll paste it into here so that we can sort of like get a sense of what we're talking about. So if I go share my screen with you now, here's what we're finding. I'm getting these collisions here. So if I look at my collisions, what I'm seeing here is that I'm really getting a lot of these collisions with the walls. They're colliding all around. Now, here we go. So the question that we ask, is there a pressure difference between the inside of the can and the outside of the can? And when the answer is like, no, there is no pressure difference between the inside and outside of the can. And as a consequence, that means then there's going to be no change in the system of the can. So now what we're going to do here is that now we ask a question. If we put the can in cold water, what happens? And here's what we do here. What we do here is that we take a container of cold water. So here we go. So now we have a container of cold water. Okay, so all we know is that this is cold water. By the way, you could do it with tap water too. It doesn't work as great. And what we do here is that we take the can and we actually turn it upside down. So when you're looking at the can, the hole now is down here at the bottom. And again, what are we seeing here? We're seeing here that this is what? This is hot water vapor. And what happens here is that when you do that, something quite dramatic happens here. What happens here is that you could imagine that you have a can, and what happens afterwards, right? What happens afterwards is that the can implodes. And I have an image of it, wherever I could find my thing here. And it looks like this here. So afterwards, what you see here is that the can actually looks like this here. Damn it. Okay. I see this can, and you can see that the can gets crushed here. It totally gets crushed. So the question is, what does the cold water do? Well, the easiest way to think about this is that, think about it this way here. Let's go back to the applet. The applet is really phenomenal here. And so when I'm thinking about this applet, here's what I'm seeing here. So look at the gas molecules. They're moving. They're colliding with the walls of the container. And then what you actually do here, when you put it into the water, the temperature of the gas molecules is changed almost instantly. Remember, it's the gas molecules. And so if I click on here, water, look what happens. Boom, all of a sudden, there's no collisions with the walls of the container. This here is almost a pure vacuum, which is very, very rare that you can actually do that here. And so what I'm going to do now is that I'm going to go in and I want to get these images and bring them into with us here. So what I got to do here is that I got to, let me grab the images first, and then I'll share my screen with you. And so let me share my screen with you now. And here's what you see here. What you're seeing is that when you're inside like this, what you're finding here is that, you know, this color is not so great. Let me see if I can get yellow to be a better color. What I find here is that this guy is a high pressure inside. So that means I have a hot water vapor that looks like this here, right? So this is hot water vapor. And what do I know here is that the hot water vapor has no pressure difference with the atmospheric pressure. And so we know that this is atmospheric pressure out here. So what happens now is that, oh, damn, I think I took a copy of this thing twice here. Let me go get, let me try this again here. Yep, unfortunately, I got to delete this guy. I got to go get this guy over here. So now what happens here is that now you instantly get what? Well, I still have the high pressure outside, right? I still have atmospheric pressure outside. And so now I have cold water vapor with no wall collisions. And so what do you get? You instantly, you create a very low pressure inside, and then you go from a high to a low pressure region, and that thing gets killed off here. That's what causes the implosion right there. The sudden change in temperature. I got to show you this video before we go. So let me set this video up. This is a very well-known video.
This unforgettable vacation memory.
Unfortunately. So here, let me go share my screen with you here. And this is actually a live situation that actually happened. So the first time it happened, it wasn't caught on video. And then numerous people have done it afterwards. But what ended up happening is that these people went in and steam cleaned a container, one of these tanker trucks here. And as they steam cleaned the container, what you ended up finding here is that they steamed it the night beforehand. And so they closed it right away, and they had a whole bunch of hot gas in the car. Overnight, the temperature dropped low enough that it cooled. So now we have a high pressure, low pressure region. And The rest is history. So this is the French people actually doing this, and check this out. By the way, that's not a can, that's a freight car. It almost looks fake, but it's not. Right? That's a very, very impressive. There's really two things here. Not only do you reduce the kinetic energy of the gas molecules very quickly due to temperature, they also occupy now a smaller volume. And as a consequence, you then get that high versus low pressure region. And like I said, systems always move to that situation. Like I said here is that, over time, as soon as people found out that that you could do this with trains, then people did it on purpose when they were going to decommission here. Now, what the video that I showed you, I didn't show you, there's a much better one, but it's much, much longer. So this is what ended up happening. The first time it happened, this is what happened. So now we're talking about temperature still. So the night before, the tanker cars were steam cleaned. Wow, for some reason, I'm having trouble spelling cleaned. The night before, the tanker's cars were steam cleaned inside. So what happened here? What did they do? They removed the air and replaced it with hot water vapor. So what they immediately did afterwards, and then what they did here is that then they sealed the tanker truck or the tanker car without letting it cool off with doors open. And so then nature took its place. So what happened? The night got cold, right? So then what happens next here is that the night gets cold, and as it gets cold, you then reduce temperature of water vapor. And once you reduce the temperature of the water vapor, what happens? You then get the implosion slash crush of train, which is, you gotta admit that must have really pissed off a lot of people. I remember many years ago when I was teaching at Fresno State, I was talking about this in one of the classes that I was teaching. And some guy said, well, yeah, you could do that to a little can. And he said, but I bet you can't do it to a 55-gallon container, which are built much, much more sturdy. And I says, I bet you I can. And we ended up betting in orange. So sure enough, turns out that his family owned a ranch. They had 55-gallon containers. We heated the can. Okay, we heated the can. Then what happened here is that we sealed it, and then we took a water hose and just started cooling the can. And the process happens instantaneously. It's like boom, and it's done. And sure enough, I got an orange out of it.